Welcome to Calculus 173. During this class, we're going to focus on integrals, which is a term that you've never heard of. I'm going to slowly introduce that term during this PowerPoint. It's going to be a very conceptual PowerPoint, not tons of math, just more about thinking. Don't panic if you don't fully understand this. This is just an introduction to get your mind thinking about integrals. All right, did you know this h of t right here represents the height of a ball being tossed? We can call this the position function. So let's go ahead and call this the position function. Did you know that if I take the derivative of the position function, I actually get the velocity function? I bet you didn't know that. It's pretty amazing, actually. So this becomes a negative 9.8t. All right, I brought that down, subtracted 1. And derivative of 19.6t would be a 19.6. Derivative of that is 0. Okay, so if I take the derivative of the position function, I get the velocity function. Okay, now did you know if I take the derivative of the velocity function, I actually get the acceleration function. Okay, derivative of this is a negative 9.8, and that's it. And this actually makes sense, because if any of you take in physics, then we know that acceleration goes down, hence the negative, and it's 9.8 meters per second squared. Acceleration is a constant. Okay? I'm going to now introduce this brand new symbol, and it's the integral symbol. It looks like this. And I can say that the integral of acceleration is actually equal to velocity. Notice how I just said that statement. And then I can say that the integral of velocity is equal to the position function. Notice I went in that direction. So notice how that integrals goes in the opposite direction. All right, let's go ahead and write some takeaways from this slide. Again, I know that you're going to be a little confused after this video. This is conceptual. This is just an introduction. Don't panic. Try to absorb as much as possible. So if we take the derivative of our position function, we get our what? Velocity, right? Derivative of position gives me velocity. But also, the derivative of velocity gives me the acceleration function. However, I'm telling you that the integral of velocity gives me my position function, and the integral of my acceleration gives me my velocity. Do you notice how from this statement to that one, do you notice how they've swapped? This went from h to v, and this one went from h to v in this direction. Similarly, we're going from v to a, and then we're also going from v to a in this direction. So integrals and derivatives are the opposite direction. So derivatives and integrals go in the opposite direction. Okay, and the other takeaway is that if we take the derivative of position, we get velocity. If you take the derivative of velocity, you get acceleration. All right, let's go ahead and let's take a look at this slide. So here, what would happen if I try to do the area of this rectangle? So if I shade this picture in. Okay, well that would be base times height. In this case, it would be 5 seconds. See how this represents right here, 5 seconds, times our height of this rectangle, which would be 10, but our units are velocity, meters per second. Okay, so I'm doing 5 seconds times 10 meters per second. Well, what happens to our seconds? They cancel because they are on different sides of the division symbol. And our answer here would actually be equal to 50 meters. Interesting. So what's our takeaway here? Our takeaway is that if I have the velocity function graph, if I have velocity graphed, then the area under the curve is the distance traveled, or you can think of that as the change in position. Well, how does that connect to what we just learned? And again, this is conceptual, don't freak out. But if I take the integral of my velocity, that's equal to my position function. So notice here that I have found my distance for the change in position. So in other words, and this is huge, this is going to carry through the entire unit, put a big old star here, the area under the curve is the integral of the function. Okay, because when we took the area under the curve of velocity, we got the distance, or that change in position. Okay, again, very, very abstract. I realize that. All right, next question here says a person is driving on the highway. The car they are driving is moving at a rate of 65 miles per hour. This is a velocity because you're giving miles per hour. At 1 o'clock, the driver presses the cruise control on the car and then lets the car move down the highway at a steady rate for 4 hours. So let's draw this graph. We'll call this 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock. Okay, and then we're going to talk about going 65 miles per hour. All right, well, we're going to press cruise control, so we're going 65 miles per hour this entire time. I guess I don't really need a line right there, do I? All right, so draw this graph. Look, I've done it. Yay me. Find the area under this curve. Well, now I can go ahead and draw this and find the area of the curve. Okay, well, that's going to be 4 hours, that's my base, times 65 miles per hour. Well, notice my hours cancel, and I'm just simply left with 4 times 65, which is going to give me an answer of 260 miles. Okay. Find the slope of this curve. Okay, well, the slope of this curve is 0. What do each of these numbers mean? Well, think about this. This is my velocity function, and you just asked me to find the slope. Well, what's the slope of the velocity? It's acceleration. So we just found that the slope of velocity is 0. So we just found that the acceleration is 0. And that totally makes sense, right? Because you're on cruise control. You're not accelerating at all. Okay, how far did they travel in 4 hours? Well, we know that the area under the curve, or the integral of velocity, is going to go ahead and give me that distance traveled. So we've already found the area under the curve in part B. They traveled 260 miles. All right. So Calc B goes in the opposite direction. What does that mean? Well, we've talked about that a little bit. We mean basically if I had the integral of acceleration, it gives me velocity. If I had the integral of velocity, that would give me the position function, which we can either use h or p there. This is oversimplified, but the integral of 1 over x is going to be equal to ln x. because the derivative of ln x is 1 over x. And again, this is just an intro, please don't panic. So I can say that the integral of f prime of x is going to be equal to f of x. Okay, in other words, if I take the derivative of this thing, it should be that right there. If I take the derivative of this, it should be that. If I take the derivative of velocity, it should be that. If I take the derivative of my position function, I should get velocity. Okay, so those are our takeaways, but there's one more as well from this whole slide. You should have also learned that integrals represent the area under a curve. And more specifically, if you have a velocity function that's being graphed, the integral, or the area under the curve of the velocity function, is going to be that distance traveled. Or you can think of it as the position, how that's changed. Quite a bit to think about. Now, in our next video, we're going to start taking the area under curves, but let's be honest, we're not always going a constant rate. Sometimes we're accelerating, all right, and sometimes our velocity changes. And so we're going to start thinking about how could we take the area under the curve? How could we actually calculate that? All right, thanks for watching. I know it was a little challenging, but just get your mind thinking about integrals.